All right, so I'm trying to do something fancy with the iPad, which means invariably in the middle I will get really confused and we'll have to stop and I'll have to figure out what's going on. So yeah, so in theory, I'll be able to display a little more than just like a little more. Yeah, okay. But for now, okay, the first thing I want to do is I have some old computations on the left here. So these are all of the tilings of the m equals 2, k equals 2, n equals 6 amplituhedron. So right, each one of these bicolored subdivision tells me a tile. Yeah, so this picture is a tiling. Each one of these is a tile, and then there's a little red edge if the two tiles share a facet. Okay, I haven't told you. That's correct, yeah. So we're also talking about positroidal, finest positroidal subdivisions of delta 3/6. That's right. And you can see up at the top, there are 4 special ones. These come from fixing a base triangulation and then coloring 2 triangles black in all possible ways. So that's kind of the nice family of tilings that I talked about in the Q&A if you were there. And then the rest don't have this structure, but they exist nonetheless. Okay, and so here you get a feeling for how the pieces fit together. They look kind of different. We don't know how to predict. I don't know how to produce this picture except to ask my computer. So we don't have any theory behind exactly what this combinatorics is, but we know the story is the same for the m equals 2 amplituhedron and this hypersimplex. And yeah, so one can do computations and produce pictures like this. Okay, so I just wanted to give kind of a concrete, like this is, I think, up to cyclic rotation, all of the tilings for that particular amplituhedron. Okay. Right. Okay, so what did we do last time, yesterday? So I spent a little bit of time yesterday talking about sort of like general stuff. Okay, so just as a reminder, in the background this whole time, we have the amplituhedron map from the TNN Grassmannian into another Grassmannian induced by matrix multiplication. Okay, and we talked about what are the right coordinates to study the image of this map, and the answer was not the Plücker coordinates here, but instead these twistor coordinates, which were defined like this. And I also took the trouble to tell you about twistor coordinates in a different way. So I defined a second like amplituhedron-ish map, z tilde tilde. And all that this was the amplituhedron map followed by an embedding of this Grassmannian into a much bigger one, into GRMN. Okay. And this embedding, this iota, it depends on your matrix Z. Okay, and I said, well, sometimes it's very useful to think about this Z tilde tilde map instead of the Z tilde map. And I thought about it a little bit more last night, and I figured out why it's useful. So, right, so we had this helpful lemma, which we used. So what was this lemma? This lemma says if you have some point in your domain, so some a in here, and you pick a point in your codomain of z tilde tilde, so just some y in this GRMN, how do you know if y is the tilde tilde image of a? Well, all you have to check 2 things. The first thing you need to check is that y is perpendicular to a. Okay, and then the second thing you need to check is that y is contained in the column span of the Z matrix. And thinking about it like this is somehow very helpful because you have pulled the Z out. So like if we're just thinking about the Z tilde map, like when is x in GRK k plus m, when is like Z tilde of a equal to x? Well, if x is equal to a times z, right? Sorry, I just did that wrong order. Z tilde a equals x if x is equal to a times z. So to check this condition, I need to know something about a, I need to know something about z, and I need to combine this information. If I think about the tilde tilde map, somehow I'm checking something about a, and then separately checking something about z, or its column span, and somehow this is very clarifying to kind of pull the z and the a apart. So I think that's why, yeah, this is the philosophical reason why this tilde tilde map is more useful. Okay, what else did we do last time? I spent a long time on the combinatorics of tiles for the m equals 1 and m equals 2 amplituhedron. So we gave semi-algebraic descriptions in terms of signs of twistor coordinates, or equivalently, if you want the z tilde tilde version instead, inside of the image of z tilde tilde, so this GRMW, we could cut out the image of z tilde tilde by specifying signs of Plücker coordinates. Sorry, we could cut out these tiles inside of that space by specifying signs of Plücker coordinates. Right, and then I didn't actually talk that much about tilings. I mean, I said, okay, we have this characterization for m equals 2 of exactly what the tilings are related to the hypersimplex. Maybe what I should mention is, like, proving stuff about tilings is way easier once you have a semi-algebraic description of the tiles. One thing you have to check, for example, for a tiling is, I have two tiles. I think that they show up together in a tiling. I want to know that their interiors are disjoint. And semi-algebraic descriptions are sometimes very useful to prove disjointness, right? Because maybe there's like a hypersurface which separates them, and they're definitely disjoint. Okay, so any lingering questions about this m equals 1, m equals 2 story? I'll say, so today is about higher m. Based on the Q&A yesterday, you maybe won't be surprised that I'm going to skip m equals 3 and really start, like, odd m is bad, so I'm going to, like, higher m really starts at m equals 4. And, okay, here's the first time I try to be fancy. Okay, so, yeah, so let's think about, let's, like, return to our original question about m equals 4. Oh, also, is the size okay? Does this seem small? Okay, no, okay. Okay, so for m equals 4, what we want to show or need to show that this BCFW recursion gives tilings. If I were clever, I would have done some copy and pasting, but what was the BCFW recursion? Well, I drew pictures for you the very first day, so what I was supposed to do is I was supposed to pick I, and then the recursion says some amplitude is a sum over some graphs G prime. So G prime comes from an n-1 point computation. And so to upgrade it to something that makes sense for n, I'm just going to add a new boundary vertex I. And then I have this more complicated piece where I'm summing over a lot of things. And my picture also looks more complicated. So I've got sort of this core in black, and then I have two blobs attached to it. Okay, and I is here, J is there, and got a left blob, so that's also a graph that came up in a previous computation. And then I also have a right blob. That's a graph that came up in a different previous computation, and I'm kind of attaching them. Okay, so this was the BCFW recursion. And right, I'm not telling you all the information, but I'm sort of, this graph over here has a k statistic, and this graph over here has a k statistic, and they need to add to k minus 1, something like that. But it's a big sum. The pieces that I get are like this. And we want to show that, you know, all of the things, we want to understand why all of the graphs that show up in one of these formulas, once I do the recursion all the way down, actually gives me a tiling. So sort of step 0 is, well, why do the graphs that I see here, why are they tiles? Why do they represent tiles, right? So why do those positoid cells map injectively to the amplituhedron? And okay, well, we had a little bit of practice last time proving some things were tiles. This was an m equals 2. We like picked some really nice representative matrices, and all of the rows of this representative matrix had only like 3 entries. And then we made some arguments about orthogonality. We could recover those 3 entries of the matrix from the image under the z tilde tilde map. So okay, we try to just do the same thing here, but you run into something sort of, well, not bad, I guess, but something more complicated. So you start to do the simplest sort of graph that you could get from one of these BCFW formulas. So this is when I just take this picture And on my left-hand graph is going to be empty, so I'm just going to erase it. And my right-hand graph is not going to be very complicated. It's just going to be this. Okay, so this is a graph that comes up from the BCFW recursion. I want to invert the z tilde map on this particular cell. And when you do this, yeah, so ZG is a tile, but inverting the z tilde map restricted to this cell uses not just one of our twister coordinates, but a quadratic polynomial in twister coordinates. So we see something nonlinear for the first time. So in particular, I see the twister coordinate, I see the quadratic polynomial 1, 2, 4, 7 times 3, 5, 6, 7 minus 1, 2, 3, 7 times 4, 5, 6, 7. Okay, so I have to use this particular quadratic polynomial to invert the z tilde map on this tile. And if I wanted to describe the tile in a semi-algebraic way, I would actually need to demand that this quadratic is negative. Okay, so that's a necessary condition to kind of cut out my tile in the ambient Grassmannian. And this opens up a whole can of worms. Like, as long as in m equals 2, we didn't see any quadratics, we just saw the twister coordinates. That was all we needed to cut out our tiles. Same thing in m equals 1. And twisters, like, these are the functions that I picked. I like understand them. Once you start to get higher degree things, it's like, well, how? I don't know. Which things do you need to use? What sorts of polynomials are showing up here? Right. So this is a big obstacle. Suddenly, starting at m equals 4. I mean, okay. I think this really starts at m equals 3, but we don't think about m equals 3. Starting at m equals 4, you need high degree polynomials in the twisters to invert the Amplituhedran map. Okay. So this is one difficulty. Another difficulty is, honestly, this recursion, like the way we've been thinking about tiles, this recursion really makes very little sense geometrically. So what I mean is, like, what's supposed to happen is, like, what I plug in here, this is a graph representing a tile for a much smaller k and n. And then this one also is a graph representing a tile for a much smaller k and n. And somehow I'm like gluing these two graphs together in some way. And it's not at all clear why, like, these are all different z tilde maps. The z's have different dimensions. They don't like play nicely with each other. It doesn't feel like there's any reason why injectivity with respect to, like, the appropriate sized positive matrix for this one and the appropriate sized positive matrix for this one should translate to injectivity for the appropriate sized matrix for the whole thing. It's just really mysterious. There's like, it doesn't feel like there's a good geometric reason that this recursion should actually keep producing tiles. Okay, so right, so let me give some stuff a name. So this graph, I'm gonna call it GL, like bow tie GR. So this is supposed to this is supposed to be like a butterfly, and this picture in the middle is also supposed to look like the middle of a butterfly. Okay, so this is just a name for this way of combining two graphs. Okay, and so I'll just write down what I said. So it's not at all obvious why, if ZGL and ZGR are tiles for their respective amplituhedra, Z of GL butterfly GR should be a tile. So this is sort of where we were. I mean, we proved that these are indeed tiles, sort of still being confused about these things. And then afterwards, we looked back and we thought, okay, maybe there's another way to think about it. And so what I'm going to tell you right now is this other way to think about it. And it will require a little bit of a detour. So for a moment, it's going to seem like I'm doing something completely different, and then I'll bring it back to the amplituhedron at the end. Yes? Mm-hmm. Yes. You don't need more complicated. Yes, as you glue, the degree goes up. Mm-hmm. How complicated is that? Yeah, so in general, the polynomials could be degree k. So this is a k equals 2 example, and we see a quadratic. They will, in fact, always be cluster variables for the Grassmannian. This is something we proved. I don't think, yeah, I think that's all I can tell you. We have a degree k polynomial. I know for other reasons that it's going to be positive on the positive Grassmannian, but actually checking the sign on some other random point, I think that's probably pretty hard. Okay, so now this other way of thinking about things. Okay, this is called vector relation configurations. Okay, and this definition is inspired by, but not quite the same as, work of Affolter, Glick, Piliavsky, and Ramasamy. Nicholas Affolter is actually at University of Vienna. He's on the participant list for this week, but I don't think is actually here in person. Anyway, if you see him later, you should tell him that you saw something that he's worked on in these lectures. Okay, so what are these? Yeah, so for the moment, we can actually just forget completely about the Amplituhedron. So I'm going to fix m bigger than or equal to 1. An M vector relation configuration, which I'm going to abbreviate as VRC, on a Playbit graph G is, okay, so this is going to be a pair of things, V comma R. So what is V? So V is a collection of vectors, one vector for each black vertex of my graph. And this is going to be a vector in Rm. Okay, so M, that M that I picked, it's telling me how big my vectors are. Okay, that's what that's what V is. And then R is going to be a collection of non-zero real numbers, which one for each edge of my graph. Okay, and these vectors and coefficients, these R's, they should satisfy some properties. Okay, so the first property is that, okay, so I have a vector on each black vertex. My boundary vertices are black. So I have a vector for each boundary vertex. I'm going to collect these into a matrix called the boundary of my vector relation configuration. The boundary of VR. So this is, I'm going to denote it like this. This is going to be, yeah, so it's going to be a vector V1 up through vector Vn. So this boundary matrix must be full rank. Some sort of mild non-degeneracy assumption. And then the more substantial condition is for each white vertex of my graph, okay, so I've got my white vertex and then it's surrounded by black vertices. And on each black vertex, I have a vector, right? So I've got like VB1, VB2, etc. And on each edge, I have one of these numbers, alpha, beta, gamma, etc. And each white vertex must tell me a real linear relation among my vectors. So if I take the linear combination alpha v beta 1 plus beta vb2, etc., that has to equal 0. So the white vertices are imposing relations. Okay, so how do I want to write this? For each white vertex, we have, if I sum over the edges that include w, those coefficients, decorating those edges, times the appropriate vector, that has to be equal to 0. Okay, so that's what a vector relation configuration is. This is not dissimilar to what Bernd talked about this morning, except he was thinking about points in projective space, and I'm thinking about points in a real vector space. So I'm kind of one dimension down from him, right? So I would be thinking of his things as planes, actually. I've just got, I just have vectors. Right, okay, so let's actually, okay, before I say anything else, let's do an example. Okay, so let me pick a graph here. Maybe I'll pick this one. Okay, this is a perfectly reasonable playbit graph. Okay, and then let me also pick an m to tell me how big my vectors are. So let me choose m equals 4. And yeah, okay, actually, sorry, let me decorate my graph a little further. Maybe I'll put in a 6 and a 7. Okay, and now, so the way I'm often going to think about these VRCs is I'm going to fix my boundary vectors and then think about how many ways there are to fill in the inside, like subject to the constraints of the graph. So I'm going to pick V1 through V7 in R4, sorry, and I'm going to pick them generically. Okay, so now I'm going to use these as my boundary vectors. So V1 goes on vertex 1, V2 goes on vertex 2, etc. And the question now is, how many ways are there to, like, how many VRCs are there with this particular boundary? Okay, so right, so I need for a VRC, I need to put some vectors like a Vx and a Vy on those black vertices, and then I also need to decorate the edges with these relations, or with these coefficients of the relations. Okay, so here's a little practice on how I think about this. So this white vertex tells me that whatever the vector Vx is, it has to be in the plane spanned by V1 and V2, right? Okay, and then if I look at Vy, similarly, it has to be in the plane spanned by V4 and V5. And then one way to interpret this white vector, yeah, so this white vertex, it gives us a lot of information, but it also tells us that Vx has to be in the plane spanned by 3, 4, and 5, for example. Okay, so what I just found out about Vx, so Vx is in the span of V1, V2 intersected with V3, V4, V5. Okay, so I picked my vectors generically, right? So I'm thinking about, I've got a 2-plane in R4, and then I've got a 3-plane in R4, and Vx has to be in the intersection of this 2-plane and this 3-plane. How big is that intersection? A generic 2-plane in R4 intersected with a generic 3-plane in R4. One-dimensional, I see. This intersection is a line. I basically don't have any choices for Vx. I sort of only have a choice up to scaling, right? Okay, and actually, I can tell you what line this is. So this is the line spanned by, okay, so abusive notation, I'm going to write the brackets even though I mean Pfluger coordinates. So it's this particular linear combination of V1 and V2. Okay, I could also write this in terms of V3, V4, V5. I'm going to run out of space. Okay. Okay, so from this formula, it's clear what I should pick Vx to be, right? I can express it in one of these two ways, but Vx, like I should choose it to be, well, I could just choose it to be this particular linear combination, for example, or any scalar of that, that's fine. And then it's also clear what I should choose for Vy. Vy should be in the span of 4 and 5. I should choose Vy to be this part of this expression. X. And then once I have made, like, let's say I make these actually specific choices for Vx and Vy, and now I can fill in all of the coefficients of my relations. So, okay, this is like somehow slower on an iPad than on a board that I don't really believe, or like that seems very strange to me. Okay, anyway, I'm just going to put stars next to the sort of interesting. So all of these things that I'm labeling with a star, these should be some particular Plücker coordinates that are showing up here. Okay, and you can match which ones. And then all of the rest of the coefficients are 1 and -1. Okay. Cool. So there's a vector relation configuration. I found if I pick a generic boundary, there's actually a unique vector relation configuration with that boundary. And if I choose a non-generic boundary, well, I'm actually not going to think about that at all. So let me, okay, I have in my notes, if I choose a non-generic boundary, you can argue there's actually no 4VRC with that boundary. So, cool, that's vector relation configurations. Any questions about these gadgets? Yeah. Yes. So, yes. Okay. Yeah. Like, why is there a negative sign up here? Yeah, so what I want to say is that Vx is equal to a particular linear combination of V1 and V2. But the way that I wrote these coefficients is like I need some sum that's equal to 0. So I've just moved Vx to the other side of the equation, and that picks me up a -1. Yeah, so there's some signs here, yeah, which are actually kind of annoying, but there's some signs. Okay, so two small things. Okay, so I said, oh, look, if you fix a generic boundary, there's like a unique way to fill in the inside. That's not quite true because we have this freedom, some freedom of scaling. So I want to get rid of that freedom, and that's going to be one of these familiar gauge transformations. I'm going to quotient out by some gauge transformations. Right, so maybe I'll just say it out loud. One kind of gauge transformation is changing my Vx by just multiplying by a positive real number. Okay, I'm going to quotient out by that gauge transformation. Another kind of sort of trivial transformation is if I take all of the, oh, I'm sorry, I was not very careful. Okay, if I rescale this by t, then I also need to divide all of the nearby coefficients by t. Okay, so, but I'm quotienting out by that. All right. The other thing I could do is I could take all of the coefficients in like a single linear relation and multiply all of those by a positive real number. That also is a gauge transformation. I'm not going to care about that kind of transformation. Okay, so let me write down. Okay, so I'm going to think about the set VRC, so vector relation configurations with size m vectors on G. Yeah, so this is going to be the m VRCs, and I'm going to think about the modulo gauge. And really, I don't want to care about the specific vectors, V1 through V7, that I fixed. I want to care about the configuration. So I'm going to allow myself to act by GLM on everything in sight, right? So I'm just going to change the underlying basis of my R to the M. Okay, so I'm going to think of these VRCs modulo this gauge transformation and simultaneous GLM action on every vector in the picture. Okay. Okay, and so just to emphasize that I'm considering VRCs like up to some symmetry, I'm going to write square brackets when I'm thinking about things up to gauge. Okay, and then the nice thing that happens, since I'm considering things modulo GLM, my boundary, like the boundary of one of my VRCs, so it used to be a matrix, but now I'm thinking I have GLM action, I have the row operations, and so now my boundary is an element of the Grassmannian GRMN. Okay? So that's how I'm going to think about boundaries henceforth, is I just need to fix some point in GRMN, and I'm going to put that on my boundary, and then yeah, I'm going to keep asking this question about how many ways can I fill in the inside up to gauge and simultaneous. Okay. So what does this have to do with the amplituhedron? Next proposition is going to tell us. Okay, so first there's a little bit of fussing. Okay, so I want to fix my Plavik graph. And okay, I'm also going to fix a choice of signs on the edges. So there's a combinatorial rule for these signs that I'm not going to tell you. They're called orthogonal Castellane signs. Yeah, so it's just some combinatorics I kind of want to brush under the rug. Okay, then, okay, right, so we're interested in inverting the amplituhedron map, and I convinced you if I use this like z tilde tilde, part of inverting the amplituhedron map is trying to decide, like, is my point in GRMN perpendicular to a point in my cell? That was part of inverting the amplituhedron map. Okay, so what this proposition says is if I pick a generic element in GRMN, the VRCs on my graph whose boundary are equal to that kind of generic element and whose edge, like whose coefficients are positive when I multiply by these signs that I chose. So VRCs of this special type. These are in one-to-one correspondence with points in the positroid cell CG that are perpendicular to my point Y. Okay, so the point is, if I'm trying to invert the amplituhedron map, if I'm trying to understand when is Y the z tilde tilde image of A, I'm really interested in understanding this question, right? And this proposition is telling me, well, I can understand how many A's are perpendicular to my Y just using these special VRCs. VRCs where I've like, the boundary is fixed, it's fixed to be this Y, and there's some sign constraints on what the coefficients of the linear relations should be. Okay, so this is a, yeah, it's a way to kind of combinatorialize this question of when am I perpendicular to something in the positroid cell. Okay. Yeah, this lecture is a bit denser maybe than the other one, so I want to pause again. Are there any questions? We'll do an example shortly. Okay, maybe I'll do the example and then we'll see if we have questions after that. Okay, so let me take the same graph that I had, whoops, before. Okay, I have the same graph I had before. And let me tell you about the signs first. So here are the signs. Plus, minus. Okay, here are the signs. I promise you there's a combinatorial recipe for choosing these. I'm not just pulling them out of nowhere, but I don't want to tell you the recipe. Okay, and the point is, if I have my point Y, and I want to know, like, could it possibly come from applying z tilde tilde to some element of this positroid cell? All I need to check is I need to put the columns of Y here, and I need to check, can I fill in the rest of the VRC? And the number of ways I can fill in the rest of the VRC, that's how many elements of the positroid cell Y could be the z tilde tilde image of. Okay? And so what we showed before, right, so we know if Y is generic, like what we said over here, if Y is generic, there's only one way of filling in the inside. Okay? And if it's not generic, there's no ways of filling in the inside. So what we said before, was, okay, for Y in GR 47, either Y is perpendicular to A for a unique A in this positroid cell, or Y is not perpendicular to any element of the positroid cell. Okay, so what this means, okay, so, right, how do I know? Okay, so this is checking half of the condition that y is the z tilde tilde image of something in the cell CG, right? So we have our lemma to figure out if y is z tilde tilde of A. All I have to check is y perpendicular to A and is y contained in the column span of Z. Okay, so what I just showed you on this slide tells me for y in the column span of Z, either y is z tilde tilde A for a unique A in CG, or it's just not in the image of CG under the z tilde tilde map. In other words, the z tilde tilde map is injective on the cell A, right? Because each y down there, it's either the image of exactly one thing or it's not in the image of anything in the cell. Okay, so we just showed, and a little painstakingly, using these VRCs, because for a given boundary, there's a unique way of filling in the inside that tells us that with a little bit of extra work, the z tilde tilde map is actually injective on the positoid cell. Okay, so these MVRCs, they're a way to prove injectivity of the z tilde map, or z tilde tilde, which is the same as the z tilde map. Okay. Does that seem somewhat convincing? This is a good tool to use. At least in this example, it helped us see, maybe in a kind of roundabout way, injectivity of z tilde tilde. That's the point of these VRCs. Yeah. Yes, that's exactly right. So yeah, I probably should have said, oh yeah, I had it written in my notes. How does this bijection actually work? Well, all I do is I take my VR and I send it to, yeah, I just apply boundary measurement using not quite the edge weights, but these resigned edge weights. Okay, so using sigma ERE. So this is the A that I get. So what's another thing that we gain here? We also gain a semi-algebraic description of the tile downstairs because, well, in this situation, I actually know, like I know not just the signs to put on these edges, but I actually know the functions to put on these edges to make the VRC, right? So this is what I sort of skipped drawing, but the coefficient on this edge, for example, is 2, 3, 4, 5, right? And the coefficient on this edge is 1, 3, 4, 5. And so now I can see in order for this, like we need that the product of the sign and the coefficient, those two things have to be positive in order for this story to work. So we see that to be in the tile, 1, 3, 4, 5 has to be negative. All right, so we're sort of, it forces certain quantities to have certain signs, and this is going to give us a semi-algebraic description of the tile in the end. Okay. Yeah, so maybe I'll just, okay. So I cooked up a gadget for you, these MVRCs. They seem like they kind of came out of nowhere. I mean, natural enough, but I don't know. What do you use them for? The point of this proposition is that you can use these VRCs to check if the amplituhedron map could be injective on the cell, right? So in order for the amplituhedron map to be injective, you need this set down here basically to have size 1. And so that means you also need this set up here to have size 1 for a fixed boundary. So VRCs are a tool to understand basically the fibers of this z tilde tilde map. Okay. Yeah, so I've totally forgotten when I started. Okay, yeah, so let me write some of that down. So this is supposed to be VRCs and the Amplituhedron. Okay, so the thing I said, so to show that something is a tile, it's enough to show, okay, first, for some y's in GRMN, and what we really want is for generic y's in GRMN. So for some Zariski open, maybe use a Zariski open set. Okay, so if I pick a generic y, what I need to show is that there exists a unique VRC with boundary y. And yeah, I think that's all I want to show. There's a unique VRC with boundary y. Okay, and this is telling me, okay, sorry, with boundary equal to y and signs of. Let me think about this for a second. I've just confused myself. I'm just confused myself about the signs, which I wasn't thinking about carefully when I wrote this. Yeah, okay. I'm being a little sloppy with the signs here. I'm going to say it like this so that I don't confuse both myself and you. There's a small asterisk here. There's probably a little bit more we need to add. Okay. So if we're interested in showing that ZG is a tile, we want to show something like, for generic y's, there's a unique VRC with that boundary. Okay? And then you want to say, okay, the image of my positroid cell actually sits inside of these generic y's where I know what's going on. Right? Okay, so it's kind of two separate steps. One step is just about this M plane and it being perpendicular to something upstairs. And then in the second step, you're saying, okay, what it's perpendicular to is actually, the second part is really saying like, okay, now we're going to only pay attention to those y's, which are inside of the image of this map that we care about. Okay. Cool. I'm going to focus mostly on this situation. So for generic y's, showing that there's a unique VRC with that boundary. This part is more of an algebraic thing to check. And then this part is more of a, turns out to be more of a semi-algebraic thing to check. So for the rest of the talk, I'm going to focus on the algebraic part, which is just if I have a generic y, how many, I just want there to be a single VRC with that boundary. Okay, and something that's very good is in this situation, if for generic y, I have the boundary uniquely determines the inside. In this situation, the coefficients in my VRC, so the r's, are actually rational functions in the Pluker coordinates of y. So in particular, when I'm imposing that these rational functions times some sign is positive, I want a VRC like that, this is going to unravel into a semi-algebraic description of my tile. So, okay. from this, if I can really say with a lot of certainty what this unique VRC is, I actually obtain a semi-algebraic description of the tile. Okay, so the point here is the VRCs are doing it all for us. They're letting us think about injectivity, and they are also simultaneously going to produce these semi-algebraic descriptions without too much extra work. Yeah, and I'm being, like I said, there's a small asterisk somewhere about the signs, which I will confuse myself if I think about too hard, so I'm just not going to think about it. Okay, so now we have a new regime to think about injectivity, to think about being a tile, and let's see what it gives us. Okay, so now I'm going to focus on this one. So I'm going to call G a solvable graph if one is true. So if for generic y's, there exists a unique VRC on that graph with this boundary, the boundary equal to my fixed y. Okay, so I'm calling them solvable because for these graphs, once you fix the boundary, the inside is completely solvable from the outside. Okay, so that's why the solvable graphs. And these are the graphs we're very interested in because we need our graph to be solvable basically to get a tile. Okay, so why I like thinking about this formulation of injectivity instead is because now solvability interacts very nicely with the recursions we've been talking about. Okay, so the first thing to notice is our example graph, this one. This is a solvable graph, right? That was the very first thing we did. We said if we fix the boundary and it's generic, then the boundary uniquely determines the inside. So this is a solvable graph. Okay, so now I'm going to scroll back to my BCFW, this like butterfly product. And before I said, okay, if this graph represents a tile and this graph represents a tile, it is not at all clear why this big glued together thing should represent a tile. But now I'm just thinking of tiles in terms of solvability of graphs, and now this gluing makes a lot more sense. So, okay, so let me think about what happens if I fix a generic boundary for this big graph, right? So I put my generic vectors here. Well, just this black part is a solvable graph. So what sits on the black part is uniquely determined by the outside that I fixed. And now, if I look at the left graph, GL, I have basically fixed the boundary of GL. So if GL is also solvable, then because I have fixed this boundary, as long as it's generic, which you have to check separately, it will uniquely determine what happens on the inside. And the same thing for G right. Now, because the black stuff is fixed, the boundary for G right is fixed. And since if it's solvable, then that means the rest of what's inside is also uniquely determined. So the recursion suddenly makes more sense. If I have a solvable thing in the middle and I kind of glue solvable blobs to it in a sufficiently careful way, I should get a solvable big graph in the end. So that's all that's happening in the BCFW recursion. Yeah, so the motto here is gluing with some care solvable graphs produces solvable graphs. And so now it's sort of, yeah, it feels a little less crazy that this recursion should keep producing tiles because all that's happening is, yeah, I'm gluing a bunch of solvable stuff together, so of course it continues to be uniquely determined by whatever I put on the outside. Cool. I want to say another thing about the BCFW recursion. So, right, okay, so this is basically like the high-level understanding, at least on my part, of why the BCFW recursion. Oh yeah, go ahead. Questions? Yeah, so so you can, okay. So there's again a bit of subtlety about signs. So yeah, okay. Let me think about how to answer this. So that is definitely the idea we are aiming for. We have not checked all of the details. So it seems like it's much easier to produce recursions for tiles. So like, how do you keep producing these nice pieces of the amplituhedron? It's a bit harder to generalize these tilings. So you would want, like, in this recursion is special because it tells me how to get a bunch of tiles and they all cover the amplituhedron in this really nice way. So it's easy to use this sort of idea to produce a lot of tiles, and it's hard to do it well enough that you're actually covering the amplituhedron in a nice way. Yeah, that's maybe the summary. Yeah, but you can swap out this black stuff, this black core, for all kinds of other things, and you'll still, that sort of thing will still produce for you more tiles. Okay, so yeah, I mean, I've mentioned before, like, I'm very much in the combinatorics and geometry side and much less on the like differential form side, but this also does give us, we can say some stuff about differential forms from here. I'm going to try to say something. It might not be that detailed. Okay, let me, might, okay. So what can I say about, yeah, like the original BCFW recursion was about some rational functions. And in the end, we somehow want to see that recursion on rational functions in the differential forms associated to these tiles. Okay, so very roughly, please do not take this as the actual truth. This is like the idea. The original BCFW recursion, okay, so there you're associating a function to each one of these graphs. So there's a function associated to GL and a function associated to GR, and you want to do something to them to get the function associated to the big thing. Okay, so what is it that you do? Okay, so remember these vectors in the middle were called like Vx and Vy, and they're uniquely determined by whatever's on the outside. Okay, so what's the function that I get for GL butterfly GR? Well, it is basically the function for GL, and where am I, like, what am I going to plug into this function? Like, this function has as input sort of not n boundary vectors, but however many things I've just highlighted, okay? And what should I put into that function? Well, I should put in the vector here, the vector here, the vector here, and at the end I put in Vx. Okay, so this should be sort of evaluated on Vi up to Vj, and then the last thing is Vx. And then I should multiply by kind of a similar thing on the right. So I had some function for gr, and I should kind of evaluate it on Vj plus 1 up through Vi minus 1. And then I should plug in Vy and Vx. Okay, and then I need to multiply by something. I need to multiply by 1 over all of the twistor coordinates using the 5 indices that touch the black stuff. Yeah, touching the core. Okay, so this is more or less what the original BCFW looked like. So I'll remind you, like, okay, so they didn't phrase it in quite this language, but they really did have these new vectors, Vx and Vy, that they sort of built from the old vectors, and it's exactly according to the formulas that I showed you before. So this, yeah, I think written in this language, maybe it doesn't appear until, yeah, okay, so yeah, I'll say the very original paper didn't write it in this language, but there's a later paper, a follow-up doing like all loop BCFW, and this is the way they write it. Okay, so this is the recursion we know that we're trying to kind of understand geometrically from the amplituhedron. Okay, so on the other hand, so that's the BCFW recursion. On the other hand, we have a differential form associated to the tile ZG. Okay, what is this form? I didn't tell you much about it before, but what it is upstairs, the positroid cell has a natural form associated to it. And how do you get it? Well, okay, sorry, I should not gesture up here. So CG has a form, and that form is a wedge over edge variables of d xe over xe. So it's the wedge of d logs of these edge variables that I used to parameterize my cell from way long time ago. So because the z tilde map is injective on the cell CG, the tile downstairs, you should think about it as being, well, it's pretty much the same as the cell upstairs, it's just the z tilde map has interfered. So what should I do to get a form downstairs? Well, basically, I should just rewrite these edge weights using some functions on the tile. And we actually know how to do that because they're just going to be the coefficients that I see in this vector relation configuration. Right, so the form that we have associated to our tile is a wedge over all of the edges of my coefficients in my vector relation configuration, these REs. Okay, and if you look at this, okay, what do the coefficients here look like? Well, if I know, like if I just look at GL by itself, it has, like if I looked at GL in isolation, just plugging in random things into the boundary, there would be some coefficients. And in this particular situation, what I'm plugging in to those coefficients, right, they're functions of the boundary, I'm plugging in, well, vi plus 1 up through vj, and vx. So what I get is I get the form for the left-hand thing evaluated on vi, vj through vx. And then I wedge it with the form for the right-hand thing evaluated on the boundary vectors that it sees. So that's vj plus 1 up through vi minus 1, vy, vx. Okay, that gives me most of the edge weights. So that's like takes care of all of the coefficients that live in here and coefficients that live in here. And then I have these guys left over, and the coefficients that I see here will be exactly those 5 twisters on the 5, like picking any 4 of the 5 indices touching the core. Wedge, I'll say d log of these 5 twisters. Okay, so even if all of that seemed really confusing, because it is a little bit recursive and annoying, if you look at these 2 formulas, you can see there's good, strong parallels here, right? So up here in my original recursion, I had something associated to GL, and I was evaluating it at this particular place. And down here, I also see I have the thing associated to GL, and I'm evaluating it at the same vectors. Okay, so we don't know, yeah, so what I can't tell you is that these 2 things like match up perfectly on the nose, but what I can tell you is that the recursions that they satisfy are literally the same. Okay, and yeah, maybe I'll leave it at that. So the other thing is one would hope that this form that I just wrote down is the canonical form of the tile. We don't know that, but we hope that it's true. So that's what I want to say about the forms. So there is a natural form associated to each tile. We hope it's the canonical form, and it's evolving according to the right recursion, like the recursion that we really wanted to see. I'll leave, that's the discussion of the form. That's all I'm going to say about that. Any questions? I have one more thing I want to say. Which is, what I did for you in this lecture is I took the problem we originally had, which was when is ZG a tile? And I translated it into a different question, which is which graphs are solvable? Okay, and now this is just a question separate from the amplituhedron, which I think is quite interesting. So if you draw for me, can you characterize for me somehow the Playbit graphs that are solvable? Or more generally, if I hand you a Playbit graph and an M, can you tell me how far away it is from solvable? So like if I fix a generic boundary, maybe I have 17 VRCs. Can you tell me that number 17 just from looking at the graph? So maybe I'll summarize this as saying we have new questions. Which G are solvable? I'll say so all of this stuff that I've been telling you is from a paper of myself with Even Zohar, Parisi, Tesler, and Williams. One thing that we do is we characterize the solvable trees. Okay? Okay, so we give a simple combinatorial condition. If my Playbit graph is a tree, when is it solvable, when is it not? And then as we discussed earlier, if you have solvable graphs, you can glue them together with some care and get new solvable graphs. So we sort of have a bunch of building blocks. We have lots of ways of gluing things together, but we don't have a good characterization of when a graph is solvable. Okay, and then I will say one more thing. This is for people in the room who like cluster algebras. It is also true, so another thing that we proved was that in the BCFW recursion, all of these REs that you see are actually cluster variables for GR4N, and they're all compatible. So you might wonder if this phenomenon holds more broadly. So I'll just say, connections between these VRCs, and in particular solvable graphs, and cluster algebras. So there seem to be we have some conjectures in this paper, but I won't go into details now. All right, thanks a lot for listening.